So let me thank the organizers once again for this splendid opportunity. Here is the title of my talk, which you have already seen. And this was done in collaboration with these two very nice guys, and it's due to appear on JCAP soon. So here is a brief outline of the talk. I'm going to give you a very brief recap of first-order vector-metric perturbations. Then I'm going to present to you the possibility of having PMFs, or primordial magnetic fields, as a possible candidate to have sustained vector perturbations at the first order. Then I'm going to present to you the generic formalism of vector-induced gravitational waves, or VIGWs. I'm going to give you the spectrum of VIGWs produced during a particularly stiff kinesion-dominated post-inflationary epoch. And I'm going to move on to some predictions for next-generation interferometric GW missions. And I'm going to conclude by pointing out some future directions that we plan to explore in the near future. Okay, so first-order vector perturbations don't quite often receive a lot of attention in the minimal, or better to say, the standard model of cosmology, and that's for good reason. Because in the absence of a proper source which can generate vector perturbations continually, these first-order vector perturbations, which are represented by this gauge invariant variable Vi, they tend to decay away very fast with cosmic expansion. And that renders them over time of negligible magnitude compared to their scalar and tensor counterparts. But things can be quite different if you have a source. And such a source can emerge possibly from the matter sector if we have a non-zero vector projected component of the spatial stress energy tensor that comes from, say, primordial magnetic fields, which are a particularly good candidate for generating such vector perturbations. So now, of course, a few words about PMFs. So over the last few decades, a lot of observational evidence has been amassed which indicate that our universe might be very weakly magnetized on very large scales. And while these PMFs on galactic scales, which are typically of the order of magnitude of the microgauss level, this can be explained on the basis of several astrophysical dynamo models, amplification mechanisms. These models are increasingly challenged on much larger scales, such as the IGM scales of 1 MPC and beyond, where we have these kinds of bounds currently. The lower bound comes from the non-observation of secondary GeV cascades, which should be generated from primary TeV scale blazars. And the upper bound is an indirect bound, which comes from CMB and currently available 21 centimeter observables like the AGES report. That might be a bit dubious, but bear with me. So these initially reported an upper bound of the nanogauss order, but over the years, this has been increasingly tightened to, say, an order of 10 picogauss or so. So right now we have two bounds, a lower bound of 10 to the power minus 16 gauss and an upper bound of the order of 10 to the power minus 11 gauss. And if we assume, the challenges that dynamo models face on these large scales indicate at a possible primordial origin for these magnetic fields. And if we assume a PMF, which is stochastic, non-helical, and Gaussian in nature, then it can be completely characterized in terms of its two-point function. It gives us a measure of the magnetic power spectrum. And on the other hand, the magnetic sector carries an intrinsic stress energy whose vector projection gives us a suitable source term for sourcing first-order vector perturbations by giving us a source term on the right-hand side, which looks like this. So this pi IV is written in terms of the co-moving amplitude of the magnetic sector, and all the time dependence has been factored out in terms of this scale factor squared, which is sitting in the denominator. And this equation has a particularly simple, elegant, exact analytic solution, which was derived by Mack et al. Way back in 2001. So you can see that the entire time dependence of the first order vector perturbation, when it's being sourced continually by the magnetic sector, which decays as 1 by a square, the magnetic field, the entire time dependence can be factored out in the form of this eta upon a square term, a being the scale factor. And you can immediately appreciate something interesting in here, is the fact that the evolution of the first order vector modes generated by PMFs depends crucially on the time evolution of the background, because the scale factor depends on the conformal time as a function of the parameter W, which is the EOS parameter. So in general, stiffer the background, slower the decay of the vector perturbation. And in absence of any source, it just decays as 1 upon a square, as in the minimal scenario. And on the other hand, in case of the most extreme possibility, so to say, which is of a kinesion-dominated background with W equal to 1, vector perturbations, according to this equation, this eta upon a square can become time independent practically. So these vector perturbations are permanently sustained. So this is going to be a very interesting possibility to us, as we'll see in a moment. And before we get right into the heart of stuff, a bit of a foreword about induced gravitational waves. So IGWs, very broadly can be interpreted as a direct consequence of the inherent nonlinearity of the gravitational field equations in Einstein's model. Because in such a model, lower order metric perturbations can act as source terms for higher order metric perturbations. And this has sparked a large body of research over the past decades. The most prominent spot being occupied by, arguably, by scalar-induced gravitational waves, where first-order scalar perturbations induce second-order tensor perturbations. And apart from that, there are several other studies. Not all of them are about IGWs. So this list is mostly about second-order metric perturbations induced by first-order metric perturbations. So you can have second-order vector perturbations induced by first-order scalars and so on. That being said, the possibility of having vectors, first-order vectors, inducing second-order tensors has been relatively little explored in the literature so far. And that is precisely the area that we wish to focus on in our work. So this right here is our general scheme. We assume the existence of a primordial magnetic field, which provides us with a spatial stress energy tensor that can act as a source term for sustained first-order vector modes, which in turn can induce second-order tensor modes. And these are what we refer to as VIGWs. So the usual starting point for that would be to have a generic bilinear source term for VIGWs, which is given in our case by SAB. This was derived using the expand package of Mathematica developed by Cyril Petro et al. And transforming to Fourier space in the helicity basis, we can immediately write, following from this equation, the mode function, the mode evolution equation for the tensor modes, where the helicity-level source scalar is given by this a bit cumbersome looking function. So I need to point out right here, before I proceed any further, that there is nothing special. I mean, there is nothing specific to PMFs about these two expressions. So these are all about generic first-order vectors inducing second-order tensors. Thank you. And the input of a PMF, in fact, comes much later, which I'll point out in due course. So we already have the mode equation right here. So now we are interested in solving for the mode function using the Green's function method preferably, and calculating the two-point function of these H lambdas, which are going to give us the stochastic gravitational background. And from that, we can obtain the energy, the spectral abundance, the spectral energy density of the GWs. So in order to do that, we have already noted that H lambda is proportional to S lambda. So the two-point function of H lambda is going to be sourced rather by the two-point function of the source scalar. And since this source is a bilinear function in the vector modes, it's going to be sourced in turn by the 4-point function of Vi. And since Vi itself is proportional to pi I, which is the vector projection of the stress energy tensor, it's going to be sourced by the 4-point function of the vector projection. And we can simplify this 4-point function in terms of the 2-point function via the weak expansion method. So this 2-point function is specified in terms of the vector isotropic spectrum. And it's precisely at this point that the input of a PMF becomes important if we wish to proceed further. Because we can model the vector isotropic spectrum if we assume the whole scenario to be driven by PMFs as a convolution integral of the magnetic power spectrum. So the calculation is a bit tedious. I have some result slides for that if anyone is interested. But for now, trust me. So this is the expression. And we can simplify this expression, compute the integral explicitly, and arrive at some approximate analytic form for this vector isotropic spectrum if we conveniently assume the magnetic power spectrum to be of the power law form, which is a conventional choice. So this AB and NB, these are the two primary parameters of a non-helical magnetic power spectrum, which originate from the underlying magnetogenesis model. At this point, we can link with some specific magnetogenesis model. In our case, we need the magnetic field to be produced earlier than the onset of the post-inflationary epoch. So we choose the conventional Rathore coupling model, where inflationary PMFs can be generated via the explicit breakage of the conformal invariance of the Maxwell action. So in that case, according to Kobayashi and Slot, the two parameters AB and NB can be recast in terms of the fundamental parameters H inflation and S, which is the non-conformal coupling constant of the Rathore model. The scale factor A inflation at the end of inflation can be computed according to this formula. So our total parameter space right now consists of the Hubble parameter, thank you, the Hubble parameter at the end of inflation, the total duration of the post-inflationary epoch in terms of the number of E-folds, the non-conformal coupling constant, and the background EOS parameter. And now, equipped with all these pieces, we are now finally in a position to be able to compute the VIGW 2-point correlation function. But before we do that, the observable quantity is not the 2-point function itself. It's the GW spectral abundance, which on subhorizon scales is related to the tensor power spectrum according to this formula. And the present day GW spectral abundance on scales which were subhorizon before the end of reheating can be related in terms of the spectral abundance at the end of reheating according to this expression, but this whole factor encapsulates the contribution from the relativistic degrees of freedom of energy and entropy. The scale at the end of reheating can be approximated according to this expression, which can be derived just based on the Friedman scaling of different components and so on. So the bottom line is that, the literal bottom line, the GW spectral abundance on small scales can be computed at the end of reheating and related to its present day value with a factor which is approximately of the order of 10 to the power minus 5. So now, before I present you with the numerical results, a few necessary approximations need to be elucidated. Because post-reheating MHD turbulence sets in during radiation domination, we might need to take recourse to MHD simulations in order to model the superhorizon part of the spectrum at the end of reheating in a more accurate manner. So to keep things analytically tractable, since this is just an initial study in this direction, we have focused for now only on the production of VIGWs during the post-inflationary epoch. So the time integral, this basically implies that the time integral runs between the end of inflation and the end of reheating. The momentum integral is relevant for only those modes which re-enter during that time. And larger scales are basically superhorizon at the end of reheating. And this basically gives us an accurate estimate of the VIGW spectrum on scales which were subhorizon at the onset of radiation domination. But what about the modes which were superhorizon at that time? So this might be a bit of a loose approximation for now, but we approximate it with the universal infrared scaling, which goes like this: k cube for omega GW. Thank you. Just maybe 1 minute. So this admittedly may lead to an underestimation of the VIGW amplitude close to k reheating from the left, but we find nevertheless that a detectably large VIGW signal can be generated even under these approximations. So these are the numerical results that we have obtained, corresponding to a particular value, a benchmark value of s equal to 2 for the non-conformal coupling constant generated during kinetic era. So W equals 1 and s equals 2, that leaves us with basically two parameters, H inflation and delta N reheating. In the left plot, we have fixed delta N reheating at two representative values of 10 and 14 and varied H inflation. I hope this is visible from the back. And on the right plot, we have just done the opposite. We have fixed H inflation at two benchmark values and varied delta N reheating. So we can see that with increasing H inflation, there is generic increase in amplitude and an increased F peak, which we identify with the scale at the end of reheating, the inverse of the co-moving horizon size at the end of reheating. And with higher delta N reheating, the opposite takes place with regard to F peak. The amplitude keeps increasing as is expected. In this plot, we have varied both parameters simultaneously in such a way so as to keep the amplitude nearly unchanged, but the peak frequency or the scale at the end of reheating, that keeps changing. According to this plot, it basically shows you as a heat map the dependence of F peak on delta N reheating and H inflation. And it is a bit difficult to arrive at an exact analytic form for omega GW, the peak value of omega GW, as a function of H inflation and delta N reheating, because both parameters not only enter the integrants in non-trivial ways, but also their limits. Nevertheless, we can compute these values. This should really be F peak at the peak frequency. So we can really compute these peak values of the amplitude at several benchmark points for H inflation, keeping N reheating, delta N reheating constant, and the opposite. And we can see that these follow approximately linear. And based on these relations, so this plot tells us that the dependence of the omega GW at F peak depends on H inflation in a polar manner. And the right plot tells us that it depends on delta N reheating for fixed H inflation in an exponential manner. So overall, we can combine them and arrive at this approximate scaling relation, where omega GW at F peak depends on delta N reheating exponentially and on H inflation according to a power law form. So here is a summary of the key takeaways of this talk. So firstly, there are four key takeaways. So firstly, we have first order vectors which can be important when they are being sourced continually by a vector projection of the matter sector. When sourced by PMFs, these vector modes can be particularly sustained during a stiff post-inflationary epoch, with the extreme scenario being given by a kinetion-dominated post-inflationary epoch. And the secondary tensor modes can be induced at higher order from such first-order vectors, according to any, which is based on the nonlinear nature of Einstein gravity once again. And this VIGW signal that results from point 3 may peak at small scales and be potentially visible to upcoming GW missions, which are interferometer based. And this study is of course not quite exhaustive, because we need to be able to better model the spectrum of VIGWs during RD on one hand, And on the other hand, we also need to be able to distinguish between the VHW spectrum on the observational front from other possible sources of degeneration, which are PGWs and SIGWs and so on. So with that, I reach the end of my talk. So thank you all for your attention.
Thank you.
If there are questions.
We have time for only a quick question.
Okay, so you have, there are two, here.
Sorry.
So you have two sources. One is the usual electromagnetic field.
Sure.
The another one is the vector perturbation.
Exactly.
So what about this electromagnetic field itself?
Right. That's a very nice question. So I guess I have the opportunity to go to a reserved slide for that. So here's a comparison that we made between the, I guess we're asking for the first order tensor modes which are sourced directly by the magnetic sector.
Yes.
So for kinetic domination, these are some of the comparative curves for identical parameter choices between the first order vector modes and the VIGWs. So these are, sorry?
Okay, yeah,
Yeah.
continue.
So what we found was that during a kinetic-dominated reheating epoch, a post-inflationary epoch in general, the first-order vector modes for identical parameter choices remain subdominant compared to the VIGWs. And this, in fact, can be explained on the basis of two key observations. The first one being that PMFs themselves decay during any sort of cosmic expansion as 1 by a square. But VIGWs, as we saw, they are sustained during kinetic domination. On the other hand, the VIGW spectrum, as its convolution integral involving the vector isotropic spectrum, that receives basically the at each value of k, it receives contributions from all values of k between k inflation and k reheating. So this, on one hand, we have a k integral, on the other hand, we have an integral over time. So based on these two observations, we can sort of intuitively explain the dominance of the VIGW spectrum over the first order PMV generated modes, at least for kinetic domination. But that being said, for softer values of the OS parameter, we found that the VIGW spectrum decays very quickly because it depends in a quartic manner on the vector perturbation.